Hello and welcome to this series of CH103 lecture. We are on chapter 17 and we are dealing with spontaneity, entropy, and free energy. So this is the third lecture series and it will be the last series of video in this chapter. So in the last section, I'm going to be covering the bottom end of this set of topics. The free energy change in chemical reactions and the dependence of free energy on pressure and free energy and equilibrium constant. Now on the last topic, I've deliberately left it out for you to follow that through the notes as are there. It's just a short segment there in the textbook. Okay, let's begin with standard free energy change. Change in free energy that will occur if the reactants in their standard states are converted to the products in the standard states. So this is the same sort of principle that we dealt with in the first law using enthalpy values. So if you look at an example, we will then follow through. Now the relationship, as we've already noted, the change in free energy, that is the standard free energy change, which is delta G naught, is equal to the standard enthalpy change minus T times the standard entropy change. So we treat this free energy as a state function and uses Hess's law, like as we have done in the discussion on enthalpy. And where are the values? The values of the standard free energy of formation are the ones that we can apply. So here's an example. If you look at the question, calculate the calculating the enthalpy change, the entropy, standard enthalpy change, standard entropy change, and standard free energy change from the thermochemical data. So these are the data that are supplied in the literature and also given for this question here. So the reaction is sulfur dioxide combining with oxygen to give you sulfur trioxide. So the mole ratio is 2 to 1 to 2. And they're all in the gaseous state. So here are the molecules, and you can see that all in the gaseous state. And these are the values that you obtain from the literature. And one note, in the literature, this heat of formation value, standard heat of formation values are in kilojoules per mole, and the standard entropy values are in joules per Kelvin mole. So beware of that. So we can calculate the enthalpy by using Hess's law. So I won't dwell too much of detail in there. We can substitute in the values from the data given, and you will end up with the value of the enthalpy change, standard enthalpy change. Okay, so let's get the answer there. It is minus 198 kilojoules. So all the values are quoted in kilojoules per mole. And so this one here will be in kilojoules because you're working in quantities that are now different from the 1 mole quantity. So you can see it's multiplied by 2 moles, here was 2 moles, and so on. So the value of the change in entropy, that is a standard entropy change, can also be calculated using the same Hess's law relationship. So the sum of the entropy of the products minus sum of the entropy of the reactants multiplied by the coefficients. So let's bring the data that is there on the table in the previous table, and you should be able to substitute that in. Watch this sign here. That sign takes care of these negative values that are stated in the last two entities. And so there you get the values. So all these are in joules per Kelvin. Joules per Kelvin, the reason is that, we have multiplied out the moles here. That's why only giving out the joules per Kelvin unit. And so you come up with your final answer is a negative 187 joules per Kelvin. Okay, so we would expect delta S to be negative because the 3 molecules of gases reactants give 2 molecules. So if you look at the equation, which I will not dwell on, you'll see that the moles of gas in the products is 2 and the moles of gas in the reactants is 3. So in other words, the positional probability or positional entropy actually decreases. So that's why you get a negative value. So that sort of agrees with that. So now we can calculate delta G using this relationship. Now bring in the values. And one thing you need to find out that when you find the value of delta, when you use the value of delta S, it is in joules. So you need to convert that into kilojoules, or vice versa. You convert this into joules so that the 2 units will match up. So it gives us this value, which is now the free energy. Now, when we have the free energy value, a negative free energy, we can say now that the process is spontaneous for sure. So here is a negative free energy change, standard free energy change, that is negative. So it should be a spontaneous reaction. Now, using free energy, we can do also the Hess's law application when we are looking at 2 different chemical reactions to find the free energy for the third. So in this case, you have to manipulate these 2 equations in order to give you the overall equation. So what do? We have to either reverse one of them or multiply by a constant in order to obtain the final value. Now, when you are reversing any equation, remember that the same principle applies here. You have to change the sign. And if you're multiplying out with a constant, you have to multiply out the value of energy with that constant. So here in this equation here, you have to reverse one of the equation, which is equation 17.6, which is the bottom part, this one. And notice that the sign will change in this. And therefore, once you have these 2 equations, you can add up to give you the overall change in free energy for this. So in other words, the change from diamond to graphite has a non-spontaneous quantity of energy here, but 3,000 joules energy. So since delta G is negative for this process, diamond should spontaneously change to graphite at 25 degrees Celsius, 1 atmosphere. However, the reaction is so slow under these conditions that we do not observe. So while it is spontaneous in terms of thermodynamics, the reaction as far as kinetics, the reaction rate may be very, very slow. Okay, now that leads us to the value of the free energy. We can also calculate standard free energy change from the value of the free energy of formation. So we also have tabulated values of free energy of formation in the literature, which are given in thermochemical tables. You can check that out. So if you're given those values, you can work out free energy by just using the Hess's law, like what we have done for the entropy. So the free energy of formation of the products minus that of the free energy of formation of the reactants. Now, the free energy of formation of an element in its standard state will be 0. So you can verify this from the table. It's given that value. So here's an example. So these are the standard free energy change of formation of each of these compounds, methanol, oxygen, carbon dioxide, and water. You can see that for pure element here is 0. And you calculate the value by using Hess's law, that is products minus that of the reactants, and that should give you the answer to this. So let me just run that through quickly, and that will give you the quantity. So in other words, we can use the enthalpy and entropy changes to determine free energy change, or you can just use the free energy of formation as shown here. All right, let's look at for non-spontaneous reactions. For non-spontaneous reactions, these are when the free energy is greater than 0. In other words, a positive value of free energy. So we need to apply external energy in order to drive these sort of reactions. And one example of this is actually in the use of electrolytic cells, or electrolysis is the process that is known for that. So electrical energy can be used to produce chemical change. This is what I've just mentioned by electrolytic cell, or some other examples given here. So this is another example. The conversion of carbon dioxide to glucose through photosynthesis is given by this reaction here. This is what you see happen in green plants, and that requires energy, and the energy really is from the sun energy. Let's look at free energy and pressure. System under constant pressure and temperature proceeds spontaneously in the direction of lowers its free energy. And what are the conditions of lower free energy? Free energy of the reaction system changes as the reaction proceeds and depends on the pressure of gas or the concentrations of the species in solution. So the equilibrium point, the equilibrium is a point where the free energy value is lowest. So if we look at that, for ideal gas, the enthalpy is not pressure dependent, but the entropy depends on pressure because it is related to the volume. Now, at a given temperature of 1 mole of an ideal gas, these are the relations that we can draw. A large entropy, because of entropy is greater than the entropy in the volume. So in terms of large volume, there's a greater entropy to the small volume. For pressure, the low pressure has a greater entropy to high pressure. These two are inversely related. And we can write out that relationship for gases. That is the free energy of any gas particle or any gas molecule is equal to the standard free energy multiplied by the change in the pressure from the standard state. So this is the free energy of a gas at 1 atmosphere. This is the free energy of a gas at a pressure P other than 1 atmosphere. So that is the calculating of the free energy change based on the standard value and the deviation from the standard value. Now, if you look at it in the reaction now, from a reactant to products in the gaseous state, this becomes a change in free energy, because change in free energy for the products minus that of the reactants, we can then apply this relationship. So the change here looks at the two different setup of the reactions, products and reactants. And now the pressure here will be the pressure of the products over that of the reactants. So here will be the logarithm term, or the Q, which is the reaction quotient. Now, one important aspect about this, R value here, when we are talking about the free energy term, is actually the universal gas constant, And because we are dealing with energy, we are going to use the 8.3145 joules per Kelvin per mole unit. Okay, let's look at one example here for the synthesis of methanol from carbon monoxide and hydrogen. These are gases going into liquid, and already you can see from positional probability or entropy, you can see that it is the reverse, because this is a liquid state, it's come from the gas state, so you expect a negative entropy here. So calculate delta G for at 25 for this reaction, where carbon monoxide given the pressure and hydrogen gas given the pressure here. So they are not under standard condition. These are 5 and 3. So how do we compute this value? We can do that from the thermochemical equations and the literature. So let's look at that, and we are going to then calculate this. So we'll start with this, and then we'll make substitutions on this part of the equation as well. So these are the values of the free energy of formation from the literature. Now we can apply the delta G for the reaction, products minus the reactants, and that gives us this value, minus 2.9 times 10 to the power of 4 joules. So let's look at that. Gas constant is R. Temperature, let's change that to Kelvin. And now let's work out Q. Q, as we are given the pressure values, so 5 and 3 here. Now based on the equation, this is squared, so we have to square this hydrogen pressure. And note that pure liquid, methanol, doesn't count in the equilibrium relationship. So now we bring all the terms together. So this is minus 2.9 times to the power of 4 and plus RT, this is RT, and log, this is natural log of 2.2 times 10 to the power of minus 2. So here we go, and that gives us this term here, minus 38 kilojoules per mole. Now this free energy term here was minus 29. This is minus 38. So in other words, this change that we have looked at, essentially it becomes a lot more spontaneous compared to what it was from the standard state. So no, delta G is significantly more negative than delta G naught, implying the reaction is more spontaneous as the reactant pressure greater than 1 atmosphere. And yes, of course, we can relate that to Le Chatelier's principle. So the dependence of free energy on pressure. Let's look at the meaning of delta G, where even when the values of delta G provides information regarding whether the system is favored under a given set of conditions, system may not proceed to pure products, and system may not remain as pure reactants. So a system will spontaneously seek equilibrium. So how does it do that? The system can achieve the lowest possible free energy by going to equilibrium, not by going to completion. So this is an example. This is the point, for example, where there is a minimum. So this is where the favorability of a reaction will go. In many cases, you will see that the position of the minimum free energy. So the equilibrium point, it occurs at the lowest value of the free energy available to the reaction system. So instead of going into the details of this, consider the following equation, hypothetical equation, where A going to be free energy of A is a gas and B is a gas. Let me just write out this reaction here, going on to B. Free energy of B is this term here, So this is the pressure term. Total free energy will be the sum of the two. So we're looking at A and B here to start with, and as the reaction proceeds, A, we're expecting it to decrease and B increase to reach that point where the free energy values of B and A are the same. When they have the same free energy values, that means the free energy of the products is equal to the free energy of the reactants, and therefore this is what essentially will come up to. The change in free energy will be the free energy of products minus that of reactants, which is going to be 0. So what does that 0? This is the point of minimum free energy value. That's at that point, that is where it is at equilibrium. So the delta G value is actually 0 at that point, at equilibrium. So if we substitute this into the relationship, delta G is 0, so you'll end up with delta G naught plus RTLN K, which is the equilibrium constant. Now, because of equilibrium, it is K. You'll come up with a very, very, very useful equation, and that is this one here. Delta G naught, that is the standard free energy change, is essentially equal to minus RT natural log of the equilibrium constant. So this is a direct relationship of the equilibrium constant to the thermodynamic term, or energy term here, free energy. So in general, this is what we would say. If the free energy change, standard free energy change is 0, system is at equilibrium, K is equal to 1. Here, if it's less than 0, it is spontaneous, K will be greater than 1. If it's greater than 0, this is less than 0, sorry. If it's greater than 0, this is K is less than 1, so it's non-spontaneous. So let's revisit this topic from what we started discussing at the beginning, that is on corrosion. Iron combines with oxygen to form iron oxide. So this is essentially the basis of corrosion or rusting. Although in many scenarios see that it is a reaction of water, which is instead of the oxygen, because you need that medium in order for this process to occur. But the same applies really. So using the following data, calculate the equilibrium constant. We can then, so you're given the enthalpy of formation values and the entropy, standard entropy values in the book. So now you can use this equation to find the value of free energy, standard free energy change. So now we substitute in the values for the enthalpy, and then we'll do the same for the entropy. We get the two values. So that's the standard enthalpy change, standard entropy change. Note the units again. This one is in given in kilojoules, and now it's converted to joules. And so as this one is in joules, so remain in joules. So in other words, I have to convert this unit to joules to be consistent. Temperature to be converted to Kelvin, and now let's bring it into the equation. So the free energy change is equal to enthalpy minus temperature times the entropy change. So substituting the two values there of the temperature and entropy, so you come with this number. So this value here gives you a negative value, very large negative. So in other words, this process is spontaneous. So rusting thermodynamically is what is spontaneous. So this reaction here, and we can work out the equilibrium constant value minus RT ln K. That is equal to 1.4 times. So you can see that let's get the value of K. Let's get the value of K. So here's the ln K is equal to 601, and K will be e to the power of 601. So this is a huge number. So this is a very large equilibrium constant. And what does that mean? Rusting is clearly favorable. That's why this is one of the major economic factor in the developed countries, or any country really, because a lot of metalware have to be taken care of because of corrosion. Now, other ways of representing the temperature dependence of free energy. So here you can look at the delta G naught is equal to RT ln K, and we know that delta G naught is equal to delta H minus T delta S. So we can rewrite this by making ln K the subject of the formula. So instead, if we write ln K as the subject, here you have delta H over RT and delta S over R, and factor out so that it looks pretty much very obvious here into the form you should be able to relate. This is a straight line. So a plot of ln K versus 1 over T is very famous, and it should be able to get a negative slope, linear, and then this slope here is equal to minus delta H over R. Yep, sorry about my delta H over R. So R is known, that's the gas constant, and therefore we can determine the value of delta H. So this is a very famous plot, and it's very, very useful. And what about this term here? That can actually be ascertained from this, where it cuts the y-axis. So that's the y-intercept. Very, very useful equation in the plot form. So this is the intercept, that is the slope, for the plot of ln K versus 1 over T. So in summary, this is what can be said. The first law states you can't win, you can only break even. That's what the first law. The second law, you can't break even. So as we use energy, we degrade its usefulness. Okay, that brings to conclusion of this third and last series of this video, and thank you for listening.